Welcome to Discussion 1, x86 and Calling Convention. Question: how are C function calls implemented in assembly? To answer this question, today we'll be looking at the concepts of the stack and calling convention. Here's a more detailed list of topics, and let's get started. So usually in this class, and for the rest of this video, we'll be working in the context of a 32-bit x86 machine. What is x86? Well, x86 is an instruction set architecture, or ISA. This means it defines the set of instructions and registers used by the CPU, as well as defining other things. Another ISA, which you may have seen before, is RISC-V. By the way, when in this class we write x86 code, we'll be using the AT&T syntax. The reason I bring this up is because sometimes you might see online some x86 code that seems different from what you've seen in this class, or seems to somehow not make sense maybe. In that situation, it's possible that they're using a different syntax, like the Intel syntax. So starting from the top, there are memory and registers. So the CPU, you can say that the CPU uses two things to execute programs. On one hand, we have memory, which is this big thing which is used for many purposes, including tracking variables and program data. On the other hand, we have registers, which are like this small set of variables stored on the CPU, which are used for some special purposes. For example, they can be used to store the location of something, or perhaps the output of a function, and so on. An important part of memory, which we'll be seeing a lot today, is the stack. So the stack is a section of memory used as a first in, last out data structure to temporarily store data during function calls. For example, the stack is used to store local variables, so variables that are declared within a function. How is this done? Well, every time we have a function call, space is allocated on the stack for local variables. When the function returns, the space is released. The space on the stack used by one function is called a stack frame. You can also think of a stack frame as kind of the local scope of a function. When we allocate space in stack, we actually allocate in lower memory addresses. This can be summarized by saying the stack grows down. For example, whenever we have a function call, the stack frame of the function being called will be lower than the stack frame of the caller function in memory. Now, how does one keep track of stack frames in practice? Actually, this is something that registers can help us do. Registers are 32-bit variables stored directly on the CPU. There are several important registers to know. Among them are the EBP, or base pointer, which points to the start of the current stack frame, the ESP, or stack pointer, which points to the bottom of the stack, and equivalently, the bottom of the current stack frame. And finally, the EIP, or instruction pointer, which points to the current instruction. Now, the first two registers here kind of point to memory within the stack, while the EIP points to within the code section of memory and fulfills this kind of fundamental purpose of letting the CPU know what instruction it's supposed to be running. Okay. So when calling a function, in a function call, we've seen that a new stack frame is created. In addition to this, there are some important details that must be agreed upon between the caller and the callee. For example, where are the arguments placed? Are they placed in stack, in the memory, or perhaps in registers? Good question. Another question is, where is the return value placed? And there are many more questions. The calling convention answers these questions. So broadly speaking, a calling convention is a set of expectations agreed upon between the caller and the callee in the event of a function call. In this class, we will usually work with a specific calling convention, which is known as the C calling convention for 32-bit x86. Let's describe it. To do this, we're going to go over the standard steps that occur when calling a function under this calling convention. So let's say I as a function want to call another function. Step 1, we push the arguments to the other function onto the stack in reverse order. By the way, when we push something onto the stack, let's say we want to push a register, what happens is first the stack pointer is decremented by 4, and then whatever we want to push is stored at the stack pointer, at the value, at the location pointed to by the stack pointer. Okay, that's the first step. Next, we'll save the instruction pointer and then change it. So first, we'll push the instruction pointer onto the stack, hereby saving it. The saved instruction pointer on the stack is called the RIP. Then we'll change the instruction pointer to point to the start of the function we're calling. Now we're in a function being called. The first thing this new function does is push the old base point onto the stack and then update it by setting it to the current stack pointer. Then the function will execute and do its stuff. When it's done, we'll have some return value. In our calling convention, this return value is expected to be placed in the EAX register. After all is done, we can restore the stack pointer to the value of the stack pointer after step 5, which happens to equal to the base point. Then we can pop the SFP off the stack into the EBP register, and then we can pop the RIP off the stack into the EIP register. After this is done, we're back in the original function. And the last thing to do in the original function is to remove from stack the function arguments that were pushed onto stack before. And that's it. By the way, some of these steps can be done in a single instruction. For example, steps 2 and 3 can be done by calling the call instruction, and step 9 is usually done by invoking the ret instruction. In order for this to make sense, it's important to go through the steps oneself, perhaps with an example. In particular, when you do this, you should always draw the stack. But for reference, we'll do an example here. There's a similar example in the textbook where they provide assembly instructions to do the steps of calling convention. That may provide some clarity, however, for simplicity, we won't do that here. So consider the following code, where a function main calls a function foo. At the function call, what's going to happen? Let's look at the stack. Say at the beginning, things look like this. In this picture, every row in the stack will correspond to a word of memory. And whenever one of these registers has an arrow pointing to a row of the stack, what that is supposed to mean is that the value of the register is the address of the first byte of the row. Okay? So the first thing that's going to happen at this function call is we're going to push the arguments to foo onto the stack. Now the arguments are 1 and 2, so first 2 is going to be pushed on the stack, and then 1. After this is done, the the instruction pointer is pushed onto the stack, the value of the instruction pointer, and then the instruction pointer is changed to the start of foo. And now we're executing in foo. The first thing foo does is push the base pointer onto the stack. Then it'll update the base pointer to the current stack pointer. After this, the function is free to do what it wants. And after a while, let's say we have the return value stored in EAX and we're ready to return. Then the stack pointer is restored to the current base pointer. And after that, the saved base pointer, SFP, is popped off the stack into the base pointer, and then the saved instruction pointer is popped off the stack into the instruction pointer. Finally, we're back in the main function, and the last thing we do is remove the arguments to foo from the stack. So this was a quick overview of what happens in the C calling convention for 32-bit x86. This is something that we'll be using frequently in this class, and to understand certain exploits, it's really important to really understand that we have this sequence of steps and what each step does in calling convention. And that's it. Thanks for watching.